Hello guys, welcome back to Maison African Motives, still on Engineering Science N1. In this platform, we've got the question which is on statics, November 2022 question paper. So we have the first question that we have, that is question 6.1, where we are given the fig 2 shows a shop sign that is suspended by two ropes. Okay, so this is our shop sign that we have, and it's suspended by two ropes. Okay, so you can see the first rope here with 60 degrees, the other one with 30 degrees. And we are given, this is the sign which has got a mass of 60 kgs. Okay. So from the question 6.11, we are given to draw, not to scale. So take note, this is not to scale, a space diagram of the sign and the two ropes, and that is 2 marks for that. Okay, so if we are to check here, we can properly see that we have got two forces which are going to act on this body that we have, which has got 60 kgs. So what we need is to know the weight of this object. So you know that the weight of the object, which is the force, is equivalent to the mass times the acceleration, which is the gravitational acceleration in this case. So you are given the mass of 60 kgs times 9.8, which is your gravitational acceleration, and you're going to obtain 588 Newton. All right. So this being the force which is acting on this body of 60 kgs, we've got two forces which are going to be the one, and this force you can just refer as F1, and this one as F2. So from the lines, we know that this is a horizontal line, which is also a horizontal line here. So these two lines, they are parallel to each other because they are going to maintain same distance throughout. So from the concept of in your mathematics, you know that you've got alternate angles or Z angles, which gives you the same angle at these 2 points. So if this is 60, this is also going to be 60 degrees. If this is 30, this is also going to be 30 degrees. Okay, so I'm going to indicate this here. Remember, we said we have got a body that is of 588 Newton. So let's see what you're going to have at the end as a diagram. So here we are going to represent this way. So remember, this is a space diagram. So you just indicate a weight. Remember, it is facing downwards. This is due to the force of gravity. So we have got our weight component of 588 Newton. All right. And if we are to check, there are two forces. That is the one that are indicated of 60 and 30. So these ones, we can just indicate them not accurately drawn. So you know that 60 degrees from this point, we are going to have something of this nature. For 60 degrees, let's just indicate this way, this direction. So that is our force. All right, so this is the one that is affected at 60 degrees, okay? So we can indicate this by an arrow, it's facing upwards. Then the other one, it was 30 degrees to the other side, so we can just indicate it this way. So this is not accurately drawn, guys, it's just a sketch. So I'm going to explain later on. All right, so this is the other force that you're going to have. So these are the three forces that you're going to have at the end. We are also referring to the weight. It's a force also. Okay, so getting back to the question on 6.12, we are now asked to calculate or to use the triangle of forces method to determine the unknown forces in the ropes. Okay, so this is the sketch that we have on the space diagram here. So I want you to see what we're supposed to have exactly. Okay, so this was question 6.11. Okay, now we move on to 6.12. So we are going to get back to this diagram here. Remember, there is a difference here between the forces of 60 degrees and 30 degrees. So let me just have a sketch now so that you can understand what is happening here. So this is 6.12. So remember, we've got the 588 Newton, the one that we actually know. So this is just a sketch, okay? So what you're going to do on your sketch, remember we are having a certain scale that you're going to use. So in this case, I'm going to show you the scale later on that you are going to use. So let's say this is 588 Newton. In between the 588 Newton, which is referred, it's going down due to the force of gravity. So it is facing downwards like this. Okay, so this will be taken from a north pole. Let's say this is our north pole like this one. Okay, so this is still in the same vertical line. You are going to connect here. There is a force which is connected at 30 degrees. Okay, which is the one that we do not know. So if we are to connect this force, this is what is going to happen. From this point, we are going to connect a force with 30 degrees. So that means we are going to have a vertical line, a horizontal line, sorry, that's a horizontal line. So remember, we have got north and south. So in between, going to this force, representing this force that we need, there must be an angle of 30 degrees. So you measure 30 degrees from this point, or you simply measure 60 degrees. Remember, the whole of this angle, okay, let's add everything and see what you're going to have. This is supposed to be 90 plus 30, okay? So 90 plus 30, that is 120 degrees. From 180 degrees, a straight line, you remain with 60 degrees. So this angle, if it is 30 degrees, you can simply measure 60 degrees from this point. So this angle will be 60 degrees. Okay. So this point, we do not know its dimension, how many centimeters that you're going to have. So you just leave it like that. Okay. But what you know is that if you are to connect a certain force from this, so if you connect this force, I want you to see what is going to happen here. We're supposed to connect the third force. So the third force is at 60 degrees. So this is what you do. You take this 60 degrees, take note, this is a triangle. You connect it to the force one here. This is the second force. So you connect it to force one like this. So here we are supposed to connect the second force, okay, at this point. But we want to know the angle. The angle is 60 degrees, as we can see from the horizontal, there is 60 degrees. So from this horizontal line, we are supposed to have 60 degrees. But take note, in between, there is a 30 degrees and a 60 degrees. So if you add these together, this is going to give us 90 degrees. Okay, so on our sketch, remember, we do not know exactly what is supposed to happen. So this sketch is going to help you at the end, because you know that in between here, there's supposed to be a 90 degrees, okay? So from this point, if we are to draw a 90 degrees, let's say this is our 90 degrees here, we are going to see that we are remaining with this angle, okay? And the angles in a triangle must give us 180. So 90 plus 60, from 180, we are going to obtain 30 degrees at this point. So we are going to take advantage on the accurate diagram. We are going to take advantage of the 588 because this one we are given. Okay, so let me show you what it's supposed to be like, okay? So this is the accurate diagram now. So you represent our north pole. So on this north pole, this is where we are going to have all the forces, okay? So let's say we are going to mark from this point, okay? This is our point, our reference point. Using a scale, let's say 100 Newton to represent 10 millimeters, of which 10 millimeters is same as 1 centimeter. So it means to represent 588 Newton, we divide by 100. So it is going to be 5.88 centimeters. All right. So you measure 5.88 centimeters, which is somewhere at this point. So here, I'm just going to show you, maybe we have got it at this point. All right. So at this point, if we have got our 5.88, that means that is our 588 Newton. But we measured 5.88 centimeters. Take note. So like I said, since this is a reference point, what you're going to do is that you do not know these two forces, this force, which you said our second force, and the first, we do not know these values. So what you do is that you measure the 30 degrees. Let's start with it, because this is a sketch, so you can start with any angle, either 60 degrees or these 30 degrees. So if we are to measure 30 degrees from this point, okay, so let's say we have measured 30 degrees, which is the same as measuring 60 degrees from this point. I don't know which side are you going to use. If you use this side, it means this is 60. This is 150 because it's supposed to be on a straight line. So 180 minus 30 is 150 degrees, okay? So we can measure 150 degrees. So like I said, this is a sketch for me, guys, okay? So I'm not going to do this accurately. So I just need 150 degrees, which is somewhere at this point. All right. So according to my calculations here, 150 is at this point. This is my 150 degrees, okay? As you can see here, it's 150. So let's say I have drawn this angle, which is 150 or 30 degrees like this one from this point. I know that the angle here is 30 degrees, but this angle from this point is 150, okay? Then at the end of 588, there is another 30 degrees, which we said if we are to add from the 90, it's 90 plus 30, which is 120 degrees. So it's either you're going to measure 120 or 60 degrees. Okay, so let's say we measured 60 degrees. We are going to have it like this, all right, 60 degrees. 60 degrees is same as, we can take it this way. Let me rotate my ruler here. But as for you, you're going to use a protractor, all right? So I need 60 degrees, all right? 60 degrees, that's somewhere like this, okay? So this is 60 degrees that I have measured, or 120, okay? So what you're going to do is that from this 60 degrees to the point of intersection like this one, okay, this was exactly what we're going to have. These two forces, they were going to intersect at a certain point, okay? In this case, they have intersected at this point. So that point of intersection is the one where we are having the 90 degrees as for our sketch here. All right, so remember we said this angle is 60 degrees. So guys, you just do it according to the exactly, because here it's not accurately done, okay? So this distance, okay, is our first force, which is F1. So this is your F1 and this is your F2. Okay, F2 was connected, it was going up. Okay, F2 was going up, so it's supposed to be like this, going up. Okay, so what you do is that you measure from this point to this point. Remember, you've got accurate readings there. So if you measure according to the centimeters, okay, you are going to obtain 2,9 centimeters here. This is going to be 2,9 centimeters. But remember, we said 100 Newton is 1 centimeter. So what you do is that you multiply by 100 to get back to the newtons now. So this is going to give you 290 Newton. All right. The same thing for this F2, you measure it on your ruler, you use your ruler to measure, you are going to obtain something like 5,1 centimeters, 5,1. You multiply by 100 again, you obtain 510 Newton. So these are the two forces that you need, 290 Newton and 510 Newton. So that is what you are actually supposed to do. So I'm going to show you using a protractor next time, but here I was just using a ruler, so it's not accurately done, but everything I'm going to show you in another videos that you're going to have as we move on. Okay, on 6.2, it's another question where we are given, they've got fig 3 shows two forces. So we've got two forces, that is X and Z, as we can see from the diagram, separated. X is 30 degrees from this point. We can see that we've got 35 degrees and 65 degrees from another point. Okay, so the question is, determine the value of the unknown force Z. Okay, so you need unknown force Z by using parallelogram or forces method. Okay, so you're supposed to apply the parallelogram of forces. Okay, so this is what you're going to do, guys. Just take a closer look where our Z is supposed to be on top there. Okay, so what we have in this case is that we are supposed to have our final diagram as a parallelogram. So I'm going to show you a sketch again, but you are supposed to do this accurately. Okay, so I don't know what is your suitable scale, but as for me, I'm just going to apply this one. Let's take this one. Let's say 10 Newton is equivalent to 10 millimeters, which is equivalent to 1 centimeter. Okay, I want you to see what is happening here. From our parallelogram rule, we are supposed to connect this to give us a parallelogram. So if we are to take this as our reference for the 76 Newton, which is taken at 35 degrees, we're supposed to obtain something of this nature. I'm going to explain stage by stage. So let me just indicate a ruler, but it's not going to be accurately what it's supposed to be like, but I think you can just learn something from this. Okay, so you are supposed to have your North Pole. Let's say we have got our North Pole like this. All right, so this is supposed to be at 90, like this one. Okay, let's say I have got my North Pole at this point. Okay, this is where I'm taking as a reference point, and I'm going to start with this force of 76 Newton. From this point is our North Pole like this. We have got an angle of 35 degrees. This is your north, this is your east, this is your south. So from the east going to the south, we have got an angle of 35 degrees. So you measure 35 degrees, then 76 Newton, you divide by 10. Remember, 10 Newton represents 1 centimeter. So if you divide by 10, that's 7.6 centimeters. Okay, so this is what you're going to do from this point. If we measure 35, that is somewhere here. All right, let me do this. 35. All right, so let's take it this way. Maybe we can understand. So here I'm just going to indicate, guys, not accurately, because here, if I'm to do this accurately, it's going to take us time. Okay, so let's say here is where you have your 35 degrees. So like I said, this is just a sketch. Okay, but you're supposed to do this accurately. Okay, so if you are to take 35 degrees from this point, okay, so let's say we have taken 35 degrees from the east going to the south. This is 35 degrees, and this is a force of 76 Newton. So it's 76 Newton, but on this, you used 7.6 centimeters to draw this line. So this line is 7.6 up to this point. Okay, so remember, this is a parallelogram. So we are supposed to connect the second force, which is 116. But if we are to check, it's this side with 65 degrees. So we can separate this, or we can take this one upwards like this. If we are to continue with this force going up like this, we are going to have this angle of 65 degrees, which is the same as the angle here. Remember, from your lines there, we know that two straight lines, where they intersect like this, the opposite angles are equal. So this is 65. That means this angle also is going to be 65 degrees. So at the end, if you combine 35 degrees plus 65 degrees, this is going to be 100 degrees in the end. So which means these angles, they are separated by 100 degrees, which is 35 and 65. Okay, so we say this is 35, and we are going to have a continuation from this small part like this with 65 degrees. Okay, so this is the one that I'm going to indicate. Okay, so this is what you're going to do. So I'm just going to indicate, but you're supposed to measure this accurately. Okay, but as for me, guys, I'm just going to show you what you need. So let's say we have measured this and we draw. So in terms of the distance, remember, this is supposed to be, if we are to take a closer look, this is 160 Newton. So if we divide by 10, it's supposed to be 11.6 centimeters, okay? Or we can use in millimeters, okay? So if you measure, let's say we have measured accurately at this point, this is 11.6 centimeters, which is 160 Newton. So let's say you measured and this was 11.6 centimeters, okay? Remember, we measured an angle of 65 degrees here, okay? So this is 35 plus 65, which is the whole angle, is going to be 100, okay? Then our Z from our parallelogram rule is going to be taken from this idea, guys. We are supposed to formulate from the Z that we have, we are supposed to have a parallelogram. Remember, a parallelogram, we know that if we have got something like this one, let me show here, these opposite sides, they are parallel and equal. So what is going to happen is that we are going to have a force taken from this point Z. Remember, Z is upwards like this. We are supposed to have our Z upwards, going up. All right. But what is the angle that is going to separate this Z to be referred upwards? Okay. If we are to take a closer look, we are going to join these 2 points, okay? I want you to see what was going to happen. If you were to join the points here, this was supposed to be maybe somewhere here, all right. If you were to join these 2 points like this, let's say you joined these points, you measure the distance. Here it's not accurately drawn, guys, like I said. You measure the distance from this point to this point, okay? From the sketch that I did, obtained 14.9 centimeters. You are going to obtain 14.9 centimeters. And if you are to check, we are supposed to create a parallelogram like this one. So if this is 49.9, this side and this side, they are equal, okay? And these ones, they are also parallel to each other. And the secret part is that if these 2 sides are parallel and equal, these 2 angles that we have, they must add up to 180. So if you are to measure this angle, because this is now an accurate diagram. So if you measure this angle, you are going to obtain 50 degrees. So for you to obtain 180, if this is 50, this whole angle is supposed to be 130 degrees. 180 minus 50 degrees, that's 180. So here we are supposed to have 130 degrees. But remember, I told you that this is 65, this is 35, so you are now at 100. So 130 minus 100 of these 2 angles, you obtain 30 degrees here. So the line that we are going to draw, which is the same as 14.9 centimeters, is supposed to be a straight line at angle of 30 degrees. So you're supposed to draw a straight line going at that point with 30 degrees. Okay, so let's say it's like this, with 30 degrees. If we go upwards like that, it's supposed to be like this, all right? So let's draw up, it's supposed to go up and up. So this is 14.9. So you measure 14.9, okay? So if you measure 14.9, maybe it's at this point here. Yes, just not accurate, but you are supposed to do an accurate thing. So let's say this is where you have your 14.9, which is 149 Newton. Remember, we multiply by 10. So this is 149 Newton, okay? So what you're going to do is that this force of 76 Newton is the one that is going to connect a parallelogram. So if this is 76 Newton, therefore this one is going to be also 76 Newton. So what you are going to do is that if you join, this is supposed to give you 17.6 centimeters if you join these 2 points. So if you are not obtaining 17.6, then that means everything is wrong, okay? Because this is supposed to be 17.6. So I want you to do accurate diagram, okay? Then let us see what you're obtaining. You must obtain exactly these measurements that I am telling you now. If not, then it means somehow we are not in an accurate manner like that one. Okay, so we're going to have something like this. Let me just draw that straight line that I indicated as dotted lines. So let me join like this one. Okay, so this is what we are going to have. But as for me, I'm not using accurately the measurements because this ruler it does not correspond exactly with what we want. But I did this separately, and these are the dimensions that I obtained. All right. So like I said, this is 7.6 centimeters. This is also 7.6 centimeters, which is 76 Newton. Okay. So the question is, what is the resultant? Okay. What is going to be the resultant? Okay, the resultant is this Z that we have taken, that we measured from this point to this point. This was 149. This is your resultant from this point here to this point. That's where we obtained 149 Newton. So this is our Z. So Z is going to be 149 Newton, which was taken from what? From 14.9 centimeters. So if you multiply by 10, it gives you 149. Okay, so that was exactly what we're going to obtain in this case. All right, then in this case, the resultant, what about the resultant? So the resultant, you can take it from this point. This is your north, this is your east, okay? From the north going to the east this way, it's north 30 degrees to the east. So this is going to be north 30 degrees to the east. Okay, so that was what you're going to obtain in this case. I think everything is fine. We have answered everything, right? Okay. Now on question 6.3, we are given 6.3, a wheel and axial lift. Okay, so this is a wheel and axial. An axial lifting machine is used to lift a load of 1,560 Newton, the diameter of the wheel, 320, the diameter of the axial, the effort, okay? 6.31, draw a neat labeled sketch of the wheel and axial lifting machine. That is what we are given in that case. Okay, so this is what we are going to do. Okay, let me just show you everything here so that we can see the part that has got this sketch, all right? So that's here. All right. So let me just show you here, guys. Let me show you exactly. All right. So that's the diagram that we are going to have in this case. So we have got, in this case, let's label our diagram. So this D is representing the diameter that we have on the effort. So this is our effort. So we can just have this as, okay, let's write, this is our effort here. And this is where we have our load, okay, which is our W in this case, okay? And that's our axial. So we put our axial here. Okay, so this whole part is actually representing the load, which you can just write at this point. Okay, so this is, if you are to check the dimensions that we are given, according to the diameter, this was 1,560, and this diameter here was 390. Okay, then also the forces, are this the diameter? Let's check the question, guys, before I refer to this. Okay, so I want you to see here, this is, okay, so this was the lift on the load. Okay, so this is the force that we have for 1,560 and 390 on the load. Okay, so let us do this, guys, so that we can correct this. This is not a diameter, but this is actually the length, the forces that we are given. Okay, so these are the forces that we are given. All right, so we've got 1,000. All right, so this is 1,560 Newton, and this is 390. Okay, that is here. All right, at this point. Okay, sorry for that. So I just hope everything is going to be clear here, guys. It's because I'm using separate pages. That's why I'm having this. Okay, so this is your load, and this is our effort for 390 Newton. Okay, so that is what we had actually. And what else? Let's see. We have here the diameters, okay, the wheel and the axial. Okay, so remember we've got the wheel and the axial, 320 and 64. Okay, so on the wheel, this is our wheel here with 320. So this is the wheel of 320 and axial, which is 64. All right, so that's what we had, and these are given in millimeters. Okay, so this is in millimeters. Okay, so let's just show everything here. All right, so these are millimeters, okay? 320 millimeters and 64 millimeters, okay? So if we are to indicate here, guys, okay, let's get back. So these are millimeters, all right? This is not necessary, okay? So I want us to attempt the questions now that we are given, okay? That was 6.3, is it 6.3 or 6.5? Okay, so this is 6.32 now. Okay, so on 6.32, we are given the question that is 6.32. Calculate the mechanical advantage of the machine. Okay, that is 2 marks. Okay, so we need the mechanical advantage. So remember, mechanical advantage is load over the effort. So we can even use it, we can calculate here even without the diagram, guys, because we know the values are given here. So our mechanical advantage is going to be the load over the effort, right? These formulas you are given in your formula sheet. So that's the load of 1,560 Newton over the one that you are given, the effort of to lift the load. Okay, the effort needed is 390, so we divide by 390 here. Okay, so if we divide, that is going to be a 4. Okay, so you're going to obtain a 4 there. All right, 6.33, calculate the velocity ratio of the machine. Also, you're given this formula in your formula sheet. The velocity ratio is equivalent to the diameter. You can take the diameters, actually. It can be fine if you work with the diameter. So you use the diameter of the wheel, which is D over the diameter of the axle, okay? So remember, we've got this here. Let me show you on this one. This is our diameter for the wheel, okay? So this is your wheel, and this is the axle. So you take this one, divide by this one. So simply by doing that, you can have your velocity ratio. Okay, so that is the wheel here is 390 millimeters, so that's 390 millimeters over 64 millimeters. All right, so this is what you're going to have. So 320 divided by 64 is going to give you 5. So you can write this as a 5, or someone can write this as 5:1. It's like this velocity ratio 5:1, or just 5 like that. Okay, so this is what we had. Then on 6.4, we are now given a torque of a spanner. Okay, let's just remove this one. Let's just remove this before. Okay, so let's use this one. All right, so on 6.4, we are given, in this case, the torque. So we're given the torque in this case of a spanner, which is of length 650 millimeters. Okay, the nut to be torqued of value. Okay, so the torque is of what? 494 Newton meter. So take note, it's Newton meter. And this is given in millimeters, which is the distance. So the distance R is 650 millimeters, which you are supposed to convert to meters. So remember, in a meter, we've got 1,000 okay, in a meter, we've got 1,000 millimeters. So just have to multiply by 1,000, or simply millimeters here is times 10 to the exponent of -3. Okay, so if you are given 1,000 like this, you divide by 1,000, okay, to convert to meters. This number, you divide by 1,000. Or you can just multiply by 10 to the exponent of -3, which is going to give us 0.65 meters. All right, so we have got our distance, which is written as R. So the question is to calculate the force needed to torque the nut. We need the force needed. Okay, remember that torque is given as force times distance. Also, the formula you are given in your formula sheet. So it's force times distance. The question is for you to calculate the force. So for you to have the force, you can simply divide by the distance, which is R. In this case, you remain with force. So force is equivalent to the torque over the radius. That is the torque in this case of 494 over the radius, which is 0.65 over the distance, 0.65 in meters. Okay, so if you divide these two, remember this was torque in Newton meters. This distance is in meters. So meter and meter will cancel. Your answer is going to be in newtons. So you're going to obtain 760 Newton. Okay, so therefore, that is the force required, or force is going to be 760 Newton. Okay, so that's what we had to have a total of 17 marks on statics from this question paper. All right, so we are going to continue with other questions in different classes as we are revising for the exams which are yet to come from Meson African motives till we meet again.